Hello everybody. My name is Alicja Kario and I'll be talking about black box side channel leakage verification using statistical approach. So the problem that we have been presented with in QE was that provided a compiled library, we need to show that a particular cryptographic algorithm does not have a side channel, not only to detect if they are, but also prove that they don't have one. The way to do that, we turn to statistics. The problem is, though, that if you use a right tool for the wrong job, you may get results that are semi-good, but not really, not in all cases. So there may be problems. And as we go through, using statistics correctly does require quite a bit of preparation and then applying the correct methods to the data that you actually then collect. So the very first thing is when you read about a statistical test, most of them will say that they require independent and identically distributed data. What does that mean if we are talking about as normal humans, not statisticians? So the first part, the independence, is that if we have two samples, then knowledge about value from one sample does not give us information about the other sample in this set. So in other words, one sample doesn't influence the other, then they are independent. Now, unfortunately, we cannot assume that measurements that we do when we are performing the measurements on a regular PC, on a server, maybe even on some smartphone or a development board, because modern CPUs are very complex. We have data cache, we have micro-operation cache, we have branch predictors, we have instruction cache, we have CPU temperature that we need to carry about because it will influence the frequency, dynamic voltage scaling, all that stuff. Then we also have the problems with memory, like the synchronization between those clocks and like when they do synchronize, when they don't, resource contention on the OS level, and so on and so forth. So like there is a lot of things that influence the execution of the test of the algorithm that we are actually measuring. And if we are executing one after the other, then of course the first one will influence the second one. What happens if we don't take that into account? So the easiest way to account for that is to execute tests in pairs and then randomize the order in which they are executed, and then we get so-called pair tests. If we are using unpaired tests, so like we execute like 100 tests with one set of data, 100 tests with the other set of data, then we are battling with that independence. And if the correlation between those samples is negative, then this is data for a t-test, student t-test. So if the correlation is negative, then it will give us, then it will overestimate the presence of the signal, the difference between the samples. Even if there is no difference between samples, it will be showing that there is one. And on the other hand, if there is a positive correlation, then even if there is very strong signal, the samples are very much different, then it will show that there is no difference whatsoever. So if we do not take that into account, we may have errors in both directions. So in effect, unless you know what kind of correlation it is, how sensitive the test is to that particular correlation, you are basically getting garbage results, and you cannot inference anything from that. So like I said, the solution to that is performing paired samples. So we make sure that we perform the measurements in temporal proximity with each other. So if we are talking about like the CPU temperature, executing one operation and then second operation, they will most likely be operating on the same temperature of the CPU. Same if we are also randomizing in which order we do them, then if the temperature is rising, then it will again even out to 0, because like for once there will be the second one will be higher, and then for the others it will be the first that will be higher, so in the end it will average out. Identically distributed. So for that means that they have been drawn from the same population. Population is an abstract concept in this case, because like we are talking about all the possible values that you can receive. So like in practice, the whole population is the mathematical definition of the distribution that you are looking at. So like if we are talking about normal distribution, that will be that bell curve that most of you probably are familiar with. If the tests, the nice thing is that mostly the tests handle well if you do not have the underlying distribution exactly the same. They will detect that there is a difference, and this is something that we usually are interested in if we are talking about statistical testing. If we are running the or in our case, the test vectors that it actually sends to the system under test, to that cryptographic implementation that we are trying to look at. So the solution is to perform the double-blind experiment. So as I said, the information about like what is performed must not be available to the test harness. So now the other thing is that from statistics, and a signal I could have the detected if it was present there. So we need to now figure out like when the sample is large enough for our purpose. The solution to do that is we use so-called bootstrapping, which is a way to estimate the property of the sample by resampling it itself. So when we have those 100 measurements, we randomly select 100 measurements with it, with replacement, so like some values may repeat, and then see the distribution of like median for those resamples. That allows us to get the distribution of like what is the confidence interval for that specific measurement, like mean, yeah, like median, like variance of the sample, and so on. So this allows us that, like, if we have those paired differences, we calculate those differences. We get a distribution of those differences, and by seeing that the I have actually a graph for that. So yeah, so here we have those drawing with replacement. So like some values are repeated, and then we have distribution of those values. So we can say that like for 95% of those resamples, we get values between like -2 and 2. So we can say that the confidence interval for that measurement is -2 to 2. And in our cases, since we are looking for difference and we want to show that, yeah, there is none, we are looking for a 0. So if the 0 is in that range, then we know we're good. Now, when do we know when we have a sample large enough? Well, when we're executing that stuff on a PC, on a CPU, the CPU has a maximum frequency. So if the sample, if the confidence interval is below a single clock cycle, then we know that like if there is a difference, it's below a single clock cycle, but like the atomicity of the operations is at the clock cycle level. So like for a 5 gigahertz CPU, if we have a confidence interval below 0.2 of a nanosecond, we then know that there is no possibility for the code to actually be to have a side channel given the testing that we performed. So yeah, that's what I said. And now, so this is how you should be doing it. The problem is that like I'm not the first person or the only person that looked into this to see if you cannot apply statistics. And the first people that approached that was the paper from 2009, and they used Crosby, like they designed a new test which they named the box test, and in practice this is a variant of Kolmogorov-Smirnov test, and that test requires independent and identically distributed data. Authors and as well as the people that have reused that test haven't checked the data they have collected for independence, despite writing in the very paper that the test requires the independence of the samples. So again, if you collect data, it's not independent, you'll get garbage results. The other one is the DUTE-TC. Again, uses raw t-test statistics, so student t-test, and again, doesn't use the paired sample test. So we'll have problems with the independence. So the results will be garbage if once you get to the sensitive enough sample sizes. The other one is the TVLA. It's actually an ISO standard, and that one uses Welch t-test. Again, it requires independence of measurements. Nobody tests for that. Nobody cares for that. So again, if you follow ISO standards, you still will be in a big problem. RTLF's framework is one of the very newest ones. It's from last year's Unix. It's very complex and computationally intensive. Again, they say that it requires independence. Authors didn't perform the testing in a way that would even collect the data in a way that would guarantee that independence. So how we can now extend this basic testing? Because like the tests that we have talked about, those were two sample tests. So like we can have like a positive test and then a negative test and a good. But usually the algorithms that we work with have much more possible input classes of inputs, classes of errors, and so on. So like we may want to reuse at least some of the data collection. So we can actually perform. So like yeah, for example, for RSA PKCS 1.5 decryption, there may be different errors. So like we can have a padding error, we can have the length of the decrypted value being not expected, stuff like that. So like for numerical methods, it can be a case with 0, with all bits set, with random parameters, and so on. And if we want to perform this kind of testing, this is actually possible very easily with Friedman test. It's a fairly complex, but in practice it's very easy to use, and it's just an extension of the sign test. So you just perform those measurements, like you will have like a tuple with, like if we're talking about that numerical method. So you will have like sample with zeros, probably just repeated so that you can also verify that you don't have any kind of unexpected results, because like we also want to have that canary in the gold mine that will tell us that, yeah, you are actually performing the testing wrong, and the test harness does know what it's sending, so it will affect the system and the test. And then we can have those additional values like it is vulnerable or not. ECDSA, for example, for now it looks fine, but I I don't have small enough confidence intervals to say with confidence that yes, we are definitely not vulnerable. Now, limits. The problem is that to get that negative result with a 95% confidence interval smaller than 1 nanosecond on multiple, yes, so like we were able to verify both for ASA and ECDSA against like different architectures, different implementations. Like it is really like architecture agnostic and API agnostic. Like you can apply to it. You can even apply it over network, though that does apply, give you more noise sources that you need to deal with. So you will need to collect much more data. And as expected, since the data was collected in an independent way, even for very large sample sizes, like 2 billion measurements for each class, we have not found false positives because like we use a cutoff point, the p-value, as 1 in 100,000. So like for this kind of samples, we would have to like perform 100,000 measurements to actually like start seeing false positives and so on. So yes, given that we have tested just a few dozen implementations, not seeing false positives is very much expected. So if you do this kind of testing, you need to perform randomized double-blind experiment with blocking. So like this is the stuff that I talked about that you need to, like for the scaling max, so that you need to have ways to execute the test cases in a grouped manner, like where you have similar environment in which every test in a line in that matrix was executed in. And then use appropriate statistical tests. For that, I very much recommend using non-parametric ones, so sign test, Wilcoxon sign rank test, Friedman test, scaling max test. The other benefit of using them is that they are usually much less computationally intensive than the ones that do expect you to have a normally distributed data. And materials. So if you want to see the base library toolkit that we use, this is part of TLS Fuzzer, because like, yeah, we started with the Bleichenbacher against TLS servers, then started to extending it to different things. If you want to see like very simple example with password checking, like a server that just checks the password character by character, and like you can see then when the checking stopped. There is an example there. You can run the scripts yourself, see how it works. For RSA toolkit, for ECDSA, and also I've created a very simple constant time multi-precision integer library that can just do like addition, multiplication, and division. That stuff, and then I started to work on the ML-KEM, and if you want any more questions or contact about research and or help with using this kind of stuff, you can contact me on email. So thank you, and questions please. Mm-hmm, sure. Sorry, I didn't get it.
So the ML-KEM thing, the pure Python implementation was expectedly vulnerable.
Yes. Why? Because, okay, so the question was, why was it expected that the Python implementation was vulnerable? This is because in Python, everything is executed as in a virtual machine, and integers, even like very small ones, are objects where you have like bit values. Like the way that it performs all kinds of operations is very crude. So it doesn't, like if it sees that the integers are like below 32 bits, for example, it will not use a CPU instruction to perform that operation. It will use Python like higher level assembly to perform that operation. So like the set bits will leak when you perform even the simplest numerical operation. So on that kind of basis, you cannot implement any kind of side channel free code. Please.
You said that the observer has to be blind to the test. Can you go into some technical details of how you did that?
Yeah. So the question is how to ensure that the observer does not know what kind of data it's processing. The solution is fairly simple in that you first generate the test vectors, write them all into a file, and then say an application read 32 bytes from that file, send it to the server, note how fast the server replies. Then read another 32 bytes, send to the server, see how fast it replies, and so on and so forth. So like it just copies data from one location to the other and measures like the response time. Basically, the simplest way possible to do that, and that's the correct way. It's just like at the very beginning, like when you create that file, you need to already apply that randomization. So like which is the order of the test that you will be performing in, that need to be hard coded into that file, and you also cannot reuse that file. So like it's single. When you like to get more results, you need to generate a new file and run a new file against the server or like that implementation again.
Maybe to clarify that you need the test data and the interpretation of the test inputs, because you need to know like in which class
yes, so like you need to basically
come,
create.
but they need to be in separate places, so the observer really doesn't know what kind of data is it, and then you need to interpret the results based on the
yes, so like when you generate that data, you create a file that like is the actual data, and then you also create a second file which says that yes, the first 32 bytes were class 1, the second 32 bytes were class 0, then next 32 were class 2, and then we have another row and again random ordering and so on. Okay, if we don't have any more questions, thank you for listening.